Do animals see the world as we do? Picture yourself standing in a busy city square. Cars hum past, pedestrians drift by, neon signs flicker. To our eyes, that scene unfolds in rich blues, reds, and greens, every hue falling neatly into place. But just overhead on a lamppost or building ledge, a pigeon squints at the exact same vista, and what it sees is nothing like our familiar rainbow. Imagine seeing ultraviolet patterns dancing across storefront windows, or hidden color gradients rippling in the stones beneath your feet. Ever wondered how a bull perceives a matador's cape? Or how a horse senses a predator before you even notice movement? What if we could dive beneath the waves and watch fish communicate in secret ultraviolet signals? Over the next 15 minutes, we'll journey through 4 extraordinary visual worlds of pigeons, cows, horses, and fish, and uncover how rods, cones, oil droplets, and even reflective layers redefine reality for each of them. By the end, you'll see your own world with fresh eyes, forever changed by the secret life of sight. Section 1. Human vision as baseline. Before we leap into animal eyes, let's anchor ourselves in the biology of our own vision. At the back of the eye lies the retina, a delicate tapestry of cells that captures light and converts it to neural signals. 2 main photoreceptor types reside here: rods and cones. Rods number about 120 million per eye. They handle low-light vision, detecting subtle shifts in brightness and motion as dusk falls. Cones, roughly 6 million strong, specialize in color and fine detail. They cluster densely in the fovea centralis, a tiny pit in the retina's center, granting us sharp central vision. Surrounding that, the macula and peripheral retina drop in cone density and shift toward a rod-dominant arrangement, giving us a wide safety net for motion detection at the edges of our field. Our cones come in 3 flavors: short, medium, and long wavelength, commonly called blue, green, and red cones. These 3 channels mix in our brain, producing trichromatic vision and millions of distinct hues. Yet this system has limits. In dim light, cones shut down, leaving us practically colorblind at night. And we lack ultraviolet receptors, so wavelengths below about 400 nanometers vanish from our experience entirely. Beyond color, our eyes focus light through a crystalline lens, adjusting its curvature to shift focus between near and far. Iris muscles control pupil size, balancing sharpness against the amount of light entering. This dynamic interplay helps us adapt from a sunlit beach to a moonlit courtyard. Still, our field of view maxes out around 180 degrees horizontally, and clarity plummets at the edges. We trade wide scope for sharp detail, reflecting our evolutionary priorities: tool use, reading faces, and navigating complex terrain. Now that you know your eyes rely on 3 channels, imagine doubling or even tripling that information flow. How would your world change if you saw beyond our spectral bounds? Mini Hook. In just seconds, we'll reveal a bird whose vision shatters our concept of color. Segment 2. Pigeon Superspectra. Pigeons are natural visionaries, literally. For years, scientists acknowledged their tetrachromatic vision, 4 cone types sensitive to ultraviolet, blue, green, and red wavelengths. But recent research hints at pentachromacy, 5 independent channels courtesy of 2 types of UV-sensitive cones, or an additional oil droplet-filtered receptor. Each cone partners with an oil droplet that fine-tunes the light it receives, sharpening color separation. The result is a hyperspectral view more complex than our trichromatic spectrum. Perched high above our square, a pigeon's gaze decodes ultraviolet reflections off glass facades, revealing invisible signage and polarized light patterns. On a dusty pavement, the bird discerns UV-reflective pebbles and water puddles shimmering with hidden cues. In split screen, our gray sidewalk transforms into a riot of pastel arcs and ultraviolet highlights. White shirts blaze with UV logos, while asphalt gleams with spectral contrast we can't detect. This supercharged vision serves survival and navigation. Pigeons use UV markers to find water sources and roosts. Their eyes also house photoreceptors containing cryptochrome proteins, molecules sensitive to Earth's magnetic field. That magnetoreception, combined with UV polarization patterns in the sky, grants them legendary homing abilities. They navigate cities, countrysides, even hundreds of miles, guided by an internal compass that taps into light patterns invisible to us. In flight, pigeon cones fire at lightning speed. While humans process about 30 frames per second, pigeons interpret closer to 60 or 90, perceiving motion in what feels like slow motion to us. That rapid refresh helps them dodge obstacles and rival flyers in the air's three-dimensional dance. Consider this: each second, a pigeon's brain juggles 5 color channels, polarization cues, magnetosensory input, and rapid motion updates. Our vision handles 3 channels at modest frame rates. No wonder the world looks so different from that city post. From ultraviolet, piercing cityscapes, we head to open fields, where color boils down to 2 simple hues. Cow dichromatic simplicity. Cows, like all bovines, operate with dichromatic vision, only 2 cone types tuned to short and medium wavelengths, roughly blue and yellow. They lack red and green channels, so those hues collapse into muted gray or brown. That famous bull ring spectacle? Bulls can't actually see red. Their charge at the matador arises from the cape's swift movement, not its scarlet shade. In the bright arena, we see vivid crimson cloth swirling against golden sand. To a cow, that same cape looks like a dull olive or slate fabric, blending with the earth. In pasture, grass and foliage converge into a uniform carpet of muted tones. Reds fade to grays, greens drift towards yellow. But motion, the swinging cloth, the matador's footsteps, activates rods which dominate about 80% of the cow's retina, alerting the animal to any quick disturbance. This rod-heavy design grants incredible low-light sensitivity. At dawn and dusk, cows navigate pastures with ease. Where a human's color vision collapses, a cow's rods respond to even the faintest movement, an approaching dog or subtle change in wind-blown grass. Drainpipe experiments with cattle have confirmed this. When researchers placed colored balls in a field, cows failed to distinguish reds from greens, grouping them into the same color category. But when objects moved, cows responded instantly, regardless of hue. Their world thrives on motion and contrast, not chromatic complexity. In herd dynamics, bovines communicate through body posture, vocalizations, and tactile cues rather than bright signals. A rump rub signals submission, a head toss signals annoyance. These gestures, combined with motion-based alerts, guide herd behavior far more than color ever could. Yet dichromacy doesn't dull their experience. Within brownish pastures, subtle gradients in light reveal sheltered hollows and predator silhouettes. A wolf stalking in tall grass stands out as a ghostly shape. For cows, survival hinges on vigilance, not color vibrancy. Now trade that stationary field for open plains, where nearly 360-degree vision keeps prey safe. Horse panoramic mastery. Horses occupy a world defined by breadth, not depth. With eyes on the sides of their heads, they claim a panoramic field of vision nearing 350 degrees. They see nearly behind them, scanning for predators as they graze. But that advantage comes with blind spots, one directly in front of their muzzle and another directly behind their tail, where any object vanishes from view. Imagine standing beside a meadow trail. You narrow your focus on the path ahead. The horse stretches its vision in every direction except a small frontal and rear gap. That's why approaching a horse head-on or from behind can startle it. Handlers learn to speak softly, approach from the sides, and avoid those blind zones. Horses also share dichromatic color vision with cows, sensitive to blue and green but indifferent to red. To their eyes, a red bucket may look washed out yellow or gray. In show jumping, horses gauge fence distance with their peripheral vision. Their cones cluster in a band called the visual streak, optimized to scan the horizon line. Above and below that streak, rods dominate, heightening low-light sensitivity at dawn and dusk. During a gallop, their eyes blur the center of vision, but maintain crisp clarity across a broad arc, letting them track obstacles without breaking stride. Depth perception relies on subtle shading and motion parallax rather than color contrast. Field studies reveal horses detecting movement as slight as a falling leaf from 50 yards away. That sensitivity results from high rod density outside the visual streak and rapid neural processing to flag any deviation in the wide panoramic field. Within herds, horses communicate through kinesthetic signals, head carriage, ear orientation, tail swishes, rather than colorful displays. A flick of white on a flank or an earback conveys mood in a nuanced ballet of subtle visuals. We've soared cityscapes, roamed fields, and stretched horizons. Now plunge into ultraviolet, lit depths. Ultraviolet fish vision. Beneath the waves, vision transforms once more. Water sifts out long wavelengths first. Reds and yellows disappear with depth, leaving blues, violets, and ultraviolet rays to penetrate. Many fish species exploit this by evolving ultraviolet-sensitive cones, turning the ocean into a glowing ultraviolet domain. Their lenses focus UV onto dedicated receptors. Coral polyps and algae fluoresce under ultraviolet light, creating neon patterns on the reef. Fish scales display UV markings invisible to us, social signals, mating tags, or warning flashes. These UV codes help fish recognize species, age classes, or even individual mates in the crowded reef. The tapetum lucidum lies behind many fish retinas, a reflective layer that bounces stray photons back through photoreceptors. This mirror doubles low-light sensitivity, letting nocturnal fish see in near darkness. While our vision falters at sunset, these fish navigate twilight depths as if guided by moonbeams. Deep-sea species take these adaptations further. Some display bioluminescent patterns tuned to ultraviolet, employing them like secret Morse code. Predators and prey both trade flashes in a silent underwater arms race. On the other, the fisheye reveals glowing ultraviolet trails and patterns, an information-rich landscape invisible to human sight. A final note, UV patterns also warn of toxicity. Some reef fish sport biofluorescent stripes that signal stay away, warning predators they taste foul. In this hidden language of light, ultraviolet vision isn't just an advantage, it's life or death. Through 4 lenses, we've glimpsed worlds beyond our own spectrum. Pigeons navigate ultraviolet roadmaps in polarized skies. Cows graze a dichromatic field where motion reigns supreme. Horses command panoramic horizons, trading central detail for safety. Fish communicate, hunt, and warn each other in vivid ultraviolet codes. This voyage reveals a critical truth. What we see is not the entirety of existence. Our trichromatic foveal-centered sight tells only one chapter in the grand story of perception on Earth. Next time you wander through a city square, pause and wonder, what hidden patterns swirl around you? What ultraviolet cues flicker across the sky? Consider how much remains out of sight, locked behind biological filters in creatures all around us. Do animals see the world as we do? The answer is clear: no. Each species inhabits its own hidden realm, a spectral domain sculpted by rods, cones, oil droplets, and reflective layers. Join us on a visual journey to uncover the hidden worlds through animal eyes.